Welcome back, everyone. This video is going to provide you with opportunities for some extra practice problems and walk you through the solutions to those problems. This involves Chapter 9 of the Chem 110 ebook, looking at valence bond theory. This first question is one that we've actually seen before, but I'd like to revisit it in light of the new knowledge that we have. So we want to know which of the atoms in guanidinium ion have sp2 hybrid orbitals. Pause the video and try this on your own, then come back and I'll walk you through it. Welcome back. So, did you figure it out? Hopefully you did. The answer is all of them. Now, how can you reason your way through this? First of all, you need to recognize that we're missing lone pair electrons on these nitrogen atoms. Okay? That will then hopefully help you to recognize that we have a pattern of resonance. That pattern one of the patterns we looked for was having an element with lone pairs of electrons adjacent to a double bond, which is what we have. Because of that, we can draw various resonance forms for the guanidinium ion. And overall, we have a partial, it has partial double bond character between carbon and each of the nitrogens. Because there's resonance across the entire molecule, that means we have unhybridized p orbitals on each of those atoms. So this nitrogen, this carbon, that nitrogen, and that nitrogen all have unhybridized p orbitals. They all have a trigonal planar geometry, and they all have sp2 hybridization. If they did not all have sp2 hybridization, then they would not have the leftover p orbitals that would allow them to participate in resonance. Next question. Which of the following will exhibit delocalized pi bonding? Pause the video, try this one on your own. Welcome back. So, what do we mean by delocalized pi bonding? We recognize this as when there is resonance. So you should be able to tell that we have lone pairs of electrons that are missing. Remember here, these are carbon atoms, each with hydrogens attached to them. And the number of hydrogens is based on the number of bonds that are needed in order to satisfy the octets. So now we see the full molecules with their carbons and hydrogens involved. Which of these can have resonance? Well, the two patterns of resonance that we've talked about are alternating double bonds with single bonds and having a double bond adjacent to an element with a lone pair of electrons. Here we have an element with a lone pair of electrons, but the double bond is not adjacent to it. If the molecule were like that, and we had our lone pair of electrons, then we could have resonance. Okay? Here we only have one double bond, not a second one, with alternating single bond in between. So it cannot be number 2, cannot be number 1, and so it's only number 3. Number 3 does have a different resonance form, showing the lone pair from the nitrogen as if it had moved to form a double bond, and the lone pair that was the double bond here moving up here as though it were a lone pair. Remember, we're not actually alternating between these two forms, but rather those electrons are free to move across the molecule in that zone. they are delocalized. Okay? Now, what kinds of orbitals overlap to form the carbon-oxygen bond indicated by the arrow in the structure below? Pause the video and try this one on your own. Welcome back. So, how do we need to identify the orbitals involved? Well, we need to find the hybridization of each element involved. We're dealing with a carbon and the oxygen atom. This carbon has 3 electron domains, and so it is sp2 hybridized. In order for these oxygens to be satisfied, this one needs 2 lone pairs and this one needs 3 lone pairs. Now, you might think that this is sp3 hybridized because it has 4 domains. However, you should recognize that we have resonance. Because we have resonance, we have to be sp2 hybridized with a leftover p orbital. Therefore, the orbitals, the hybrid orbitals on each of these 3 atoms are sp2 hybrids with leftover p orbitals. Therefore, the orbitals involved to make the bonds are sp2 and sp2, and then the pi bond is made up of the overlap of the unhybridized p orbitals. Okay, here's another question. Pause the video and try this one on your own. Welcome back. So, what orbitals are involved here? Again, we want to identify the number of electron domains. This is a carbon atom. We know that because it's at the point. This carbon atom currently only has 2 bonds. Therefore, we need to fill in the remaining bonds with hydrogen atoms. That means this carbon atom has 4 domains and is sp3 hybridized. This is also a carbon atom. Right now it has 4 bonds, therefore it's satisfied. We don't need to include any more hydrogens. However, one of those bonds is the double bond. Therefore, it is sp2 hybridized. Therefore, the bond that is made from the overlap of those hybrid orbitals, the sigma bond, is made up of a combination of sp2 and sp3. Here's another one. Pause the video and try this one on your own. Welcome back. How do we solve this one? Again, what we need to do is determine the number of electron domains for each atom involved. We have nitrogen and carbon. The nitrogen has 1, 2, 3 bonds, and therefore needs a lone pair of electrons. Carbon has 1, 2, 3 bonds, therefore it will get a 4th bond to a hydrogen atom. The hybridization of the carbon atom is sp2 hybridized because it has 3 domains. The nitrogen atom appears to be sp3 hybridized because it has a total of 4 domains. However, you should be able to recognize at this point that we have a set of lone pair electrons and it's adjacent to a double bond. And it's in fact adjacent to 2 double bonds. Therefore, we're looking at an example of resonance, delocalized pi bonds. Therefore, in order for this to happen, we must have a trigonal planar arrangement in order for the p orbitals to line up properly. That means we have an sp2 hybridization with an unhybridized p orbital left over. Therefore, the hybridization is not sp3 but sp2. And we then have the bond that's made up of sp2 overlap, and the pi bond is made up of a p to p overlap. Okay, last problem. Pause the video and try this on your own. Welcome back. So we want to know what kinds of orbitals overlap to form the carbon-carbon bonds in the aromatic ring. In the aromatic ring, that's referring to this. Okay? The fact that it talks about a ring should give that away at this point, even though we've not really talked about what we mean by aromatic. So you should recognize here a pattern of resonance. That is, we have alternating double bonds with single bonds. That will allow us to have resonance. So we could redraw the structure with the double bonds in alternate locations. Because we can draw a valid resonance form, that means we have delocalized pi bonds. That means that the structure is planar, and therefore we have sp2 hybridization with leftover p orbitals. So the bonds are made of sp2 and sp2. That makes our sigma bonds, and our pi bonds are made up of p to p overlap. That's it for this video. Thanks for watching. Have a great day.